Here are our solutions to homework set number 2 for ECE 376. This homework set looks at assembler with a PIC 18F4620 microcontroller. Now the first problem is, suppose I've got the W register and two spots of memory called A and B. Their initial value is 13, 11, 9. Find the value after each instruction. And the first instruction, MOVF, is a read instruction. It reads the contents of A, moves it to W. So the number 11 goes to W, A and B stay unchanged. I'll do AND literal 26. This takes the contents of W, ANDs it with 26. So W is 11, and binary, that's 0000, 1011. Let's see, 26 is 0001, 1010. Do logical AND. If either bit is a 0, the answer is 0. It's only 1 when both bits are 1. So 26 and 11 is this value. That's 10. 11 and 26 is 10. That seems kind of odd. It's bitwise operation. Now add. This says take the contents of W, add it to B, put the result in B. So 10 plus 9 is 19. Put the result in B. Ones complement. Toggle all the bits of A, put the answer in W. So A is equal to 11. Flip all the bits, and that is equal to 244 or minus 12. They're both the same. Take the 2's complement of B, put it in B. Negative 20 is minus 20 or plus 244. Either answer is correct. 2's complement. And finally, subtract W from A, put the result in A. So take A, subtract 12 from it, so 11 minus 12 is 23. A is replaced with the number 23. Problem 2. Problem 2 looks at assembler code, converting C to assembler. Now, you've got a list of assembler commands. That's your shopping list. Those are all the commands that you're allowed to use. That's all the commands the processor recognizes. The challenge is how to use those very simple instructions to implement more complex tasks. For example, suppose I want to say C is 2A plus 3B plus 4. That's one line of C. That's actually going to be a bunch of lines of assembly. The first part, in C, you have to declare your variables before you use them. What the compiler does is it knows I have 3 8-bit variables. I need to assign 3 spots of memory. Kind of arbitrarily, I'll assign 0 to A, 1 to B, 2 to C. What that tells the C compiler, or the assembler, is anytime I see the variable C, that belongs at memory location 2. The next code is 2A plus 3B plus 4. This can have to do in steps. One approach is I can just say A plus A is 2A. There is an add command in assembly. So move A to W, add A to W, put the result in W. I now have 2A. Take that result, add B to it, put the result in W. So that's 2A plus B, 2A plus 2B, 2A plus 3B, 2A plus 3B plus 4. Now that I'm finally done, take W, move it to C. So this one line of C corresponded to 7 lines of assembly. Problem 2. Do the exact same thing, only now use 16-bit numbers. Now I have an 8-bit processor. I can do 16-bit adds, but the way you do that is I go left to right. So I want to take what is 26 plus 37. Say 6 plus 7 is 13, carry the 1. 2 plus 3 is 5 with a carry, 63. Same thing in assembly. You go right to left. So a 16-bit number actually has 2 bytes. It's got the high byte and the low byte. So I want to take the number 4. Well, I'm going to assign this. How am I doing this? Okay, so this is going to be A plus 1. This is A. It takes 2 bytes to store A. So A goes at memory location 0 and 1. B goes at 2 and 3. C goes to 4 and 5. And kind of arbitrarily, I'll move call the high byte correction. A is the low byte, A plus 1 is the high byte. So the first thing I want to do 2 times A. Start out with A. Move the high byte of A to high byte of C, or low byte. Move the high byte of A to the high byte of C. Now, going right to left, I'll take the low byte of A, add it to the low byte of C, put in the result in C. Take the high byte of A, add with carry to the high byte of C, and I now have 2A. Repeat. Take the low byte of B, add it to C, put the result in C, take the high byte of B, add it to C with a carry, store it in C, in the high byte of C. That's 2A plus B, 2A plus 2B, 2A plus 3B, the number 4. Take 4, add it to the low byte of C, take the number 0, 4 is 0, 4, add to the high byte of C with a carry. And after all that, I have 2A plus 3B plus 4. And notice a 16-bit operation is 22 instructions. An 8-bit instruction is 7 instructions. It's a lot more code to work with 16-bit numbers. Even more code to work with long integers. Even more code to work with floating point. Another solution, there is a multiply command in assembly. When I multiply, the result goes in 2 separate spots in memory, product high, product low. So what I could do is take the number 4, move it to the low byte of C, clear the high byte of C. So again, C contains, this is C, here's C plus 1. This is the high byte, here's the low byte. The number 4 is 0, 4. Got 4 in there. Now add to it 3 times B. So to do that, actually add to it 2 times A. Move A to W, move 2 to W. Oh, move A to W, multiply with the number 2. That produces 16-bit number in product low, product high. Take product low, add it to C, product high, add it with carry to C, the high byte. Now add in 3 times B. Move B to W, multiply W times 3. Take the low byte of the result, move it, add it to C, put the result in C. Take the high byte of the result, add it to the high byte of C with a carry. That's the multiply. A little bit more efficient. I can do 15 instructions versus the previous code is a little bit longer. So either answer is fine. Problem 3 looks at if statements. How do you implement an if statement in assembly? So here the trick are to use these compare. There's a compare of skip if greater than, skip if equal, skip if less than. What happens, it does the register versus W. So if I want to say B greater than 10, I first have to set it up. Move the number 10 to W, then skip if greater than. If B is greater than 10, I skip. On a skip, I go to the else command. If I don't skip, I do the if command. The if command is increment A by 2, move A to W, add the number 2 to W, put the result in C, jump to the end. Otherwise, I want to increase A by 5. Move the number 5 to W, add W to A, put the result in W, move W to C. Again, everything goes through W in assembly. It's a little bit convoluted, but you can get it to work. That's an if statement. That's where you use these compare, skip if greater than. The way assembly works is I skip command if it's true. And typically you're followed by 2 go-tos. This is the skip, don't skip, go-to. Let's see. Let's do an if then else statement. If, and a while loop. While B is greater than 0, if B is greater than 10, C is A plus 2, else C is A plus 5. So here's the while loop. I will move the number 0. This is a compare skip of greater than, so it's going to be B versus W. Set it up by saying first move 0 to W, skip if greater than B, so this is if B is greater than W, I skip. If I don't skip, I go to jump to the end. So if this is not true, I end the while loop. Inside, if B is greater than 10. So this is a compare skip if greater than, B versus W, move the number 10 to W. Compare skip if greater than. If it's true, I jump down to if. So here's the skip, jump down to if. If it's false, I don't skip. I go to else. The if part is C is A plus 2. Move A to W, add 2 to W, put the result in C. Jump back to while. The else part, increase A by 5. Move A to W, increase A by 5, add 5 to W, put the result in W, move W to C, jump back to while. Problem 5 is a flowchart. This is something you can expect to see on a test. Convert the flowchart to assembly. And what I prefer, makes grading a whole lot easier, is go block by block. This block is a section of assembly. That is right here. So to make a pin input, I make the tris register 1. To make it output, I make the tris register 0. So to make port B input, I take the number FF, all ones, move that to tris B. To make C and D output, I clear tris C and D. And this part just says everyone's binary. No points off if you don't include that on tests, but if you don't put that in there, your pickboard won't run. It'll think everything's analog. Next section of code, I want to start from 0. Clear port C and D, that is right here. This branch is a label. That's label 1. Keep looping while port B is greater than 0. So this is a 8-bit test. I'm going to check the 8 bits of port B greater than 0. So move the number 0 to W, compare skip if greater than. If it is greater than 0, I want to go back. So here's the skip. Go back to L1. If it fails, I don't skip. I go to label 2. So here's label 2. Label 2. Keep looping while port B is 0. So move the number 0 to W, compare skip if equals. If it is equal, I skip, and then jump back to label 2. There's my infinite loop. If it's not 0, I don't skip. I jump down to label 3. Count mod 4. So I'm just going to increase n, put the result in W. Here's one trick. Powers of 2 are actually pretty easy. To do mod 4, I just AND with the number 3. Because what that does is anything in 0 is 0. Anything with 1 is unchanged. This leaves the first 2 bits alone, clears out the high 6 bits. That's one way to do mod 4. There's other ways to do it as well. Increase and put the result in W, and W with 3, that's mod 4. Put the result in N. That's count mod 4. That's this line of code. Let's see. If N is 0 or button 0 is 1, I vote for C. So let's check is N equal to 0. Move 0 to W, compare skip if equal to N. If it is, I skip. I always go to vote for C. Otherwise, you go to test 2. Then you label test 2. Test 2. If RB0 is 1, I vote for C. That's a bit command. I want to check bit 0 of port B. Bit test skip if clear, port B 0. If it's a 0, I skip. Otherwise, if it's a 1, I don't skip. I go to vote for C. Otherwise, I vote for D, increase D, put the result in D, go back to the beginning. Vote for C, I increase C, put the result in C, go back to the beginning. So here is a voting machine where 1 out of 4 votes goes for C. Kind of a sidelight, this actually won't work as a voting machine. With voting machines, you have 2 sets of code running in parallel, made by 2 different companies. When they count the votes, the 2 votes should match up. If one of the companies did something like this, the 2 votes wouldn't match up, and I know something's wrong with the voting machine. The third test are the paper ballots. The vote total from the first code should match the vote total from the second code, should match the total number of paper ballots. If all those match up, it was probably a legit election. If something doesn't match up, you got a problem. The fourth way to test are exit polls. The exit polls should match the paper ballots, should match the 2 pieces of software in the voting machine. It's actually really hard to rig an election. They have all those checks in it. But this is part of the reason there are so many checks. If you didn't, it'd be really easy rigging elections. It's not that easy. There are checks in the system. But anyway, that was problem number 5. Problem number 6. This is code to make a LED brighter or dimmer. Convert the assembler to C code. Kind of goes block by block. The first section code is right here. To make port B input, I write the number FF to tris B. To make port D output, I clear tris D. And make everyone binary. This is label 1. That branch is a label. I want to check if port B bit 0 is not a 1, skip. So bit test, skip if set. If it's clear, I don't skip. I jump down to label 2. That's down here, label 2. Kind of one way to figure out the skip if set, skip if clear is guess. It's got to be one of the 2. And then check. If bit 0 is 0, I want to go to label 2. If bit 0 of port B is 0, I don't skip. I jump to label 2. That's correct. Now dim the lights. Move port D to the right. So rotate right, port D, put the result in W. Clear the height most significant bit. This means it's going to shift in a 0. Move that to port D. Now I'm at label 2. Is button 1 pushed? If no, skip down to label 3. So this bit test, skip if set, bit 1 of port B. If it's a clear, I don't skip, jump to label 3, so that's right. If it is set, I do a shift left. So shift left, set the first bit, inclusive OR is a way to set. Move the result to port D. I'm now at label 3. Label 3 is wait until port B is equal to 0. Move 0 to port B, compare skip if equal. If it is 0, I keep on looping. If it's not 0, I got these backwards. On 0, I jump to label 1. On 0, I got this backwards. I go to label 1. On non-zero, go back to label 3. And that is homework set number 2 for 376.